This is just kid stuff, and I know it's real. That's how I do my magic on the court.
So, what they taught us in school isn't really the way it is. And that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes!
That's how I do my magic on the court.
Yeah, I always choose the Wonder Boy first.
Well, Dr. Quantum says everybody's got it. Everybody's doing it. Doing it constantly. Each and every time you look.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment.
The first people who did these experiments, and these experiments of, crude experiments of this kind, were first performed almost 50 years ago, or more, 60 years ago. Those people were flabbergasted.
To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum.
This is just to break down your prejudice that says a particle is a particle. Now you got to understand it's a particle and a wave.
An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense.
You got to understand it's a particle and a wave. Now that you've taken that leap, let's get one step closer to the reality. It ain't either of those either. And it's both at the same time.
But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. and it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other.
We did these experiments, and we got certain results. And in the light of these results, we asked a question of the form, gee, which path could the electron have taken through this two paths apparatus? And if there are two options like that, it's just a matter of standard classical logic, there are four logical possibilities. A, B, both, neither, okay? We went through those possibilities one by one and designed an experiment in each case to test that possibility. And the answer in each of the four cases was negative, okay? It doesn't go through root A. How do we know that? Because when we put in a total of nothing box in root A, it has an effect on this particle. But total of nothing boxes don't have any effect on particles that pass through them. It doesn't go through root B for the same reason. It doesn't go through both roots because if we stop the experiment in the middle, we always find it either on one root or the other, but not both. And it doesn't take neither root because if we just block up the two roots and leave everything else open, nothing gets through. So we can systematically, piece by piece, eliminate all of the four logical possibilities, okay, given the assumption that it makes sense to ask the question, which route did it take? That's how we're forced into a position, gee, the only thing left to do here, it's analogous to, think about the case of inquiring into the marital status of the number 5. Somebody says, gee, is the number 5 married? You say, no, that's not the right thing to say. The guy says, I see, number 5 is a bachelor. You say, no, that's not right either. The guy says, well, what else is there? You say, look, the deal about the number 5 is, it's not married, it's not a bachelor. That's not a logical contradiction. The trouble here is that the whole question of the marital status of the number 5 is a question that can't sensibly be raised. That's what we're finding out about these particles. We say, did it take root A? We can eliminate it experimentally. Did it take root B? We can eliminate that experimentally. Did it take both? We can eliminate that. Did it take neither? We can eliminate that. All that leaves us with is going this route that we go with the number 5. Oh, I see. Although in this case it's astonishing. With the case of the number 5, it was easy. What this must be telling us is that it somehow fails to make sense even to raise the question in a situation like this. Which route did the particle take?
Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of 2 bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched.
So the electron is very peculiar. The electron is very peculiar in the sense that when you are not looking, electron can be here, can be there, or can be over there in the corner of this room. It can be all over this room, so to speak. But whenever we look, this is the strange thing about these electrons. Whenever we look, we always find them to be in one particular Geiger counter, although we may have a room full of Geiger counters. We never hear the Geiger counter sticking all over the room. This is the fundamentally important stuff about the electrons.
It was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
We are always the observer. But sometimes we identify with the event so much so that we even lose the aspect of the observer. That's why the materialist gets totally lost and thinks that we could do without the observer.
The physics data tells us that an object itself is really a simplification for what we call out there. One is particularly when we're looking at atomic and subatomic particles, or atomic and subatomic matter in any form. What we find is how we go to look at it, what we choose to examine it with, actually changes the properties of what we observe to be out there.
Is this the observer, and which is so intricate to understanding the wacky, weird world of quantum particles and how they react? Is this, then, the observer? And even though we cannot have a quantum field without the observation of scientists who have gone there, who have uncovered it, layer after layer after layer, they're all observers. But not one of them agree conclusively on all points in the field, because they are perceiving the field mathematically from different angles of perception.
Mathematics shows us clearly that the movement of objects are describable only in terms of possibilities, not the actual events that happens in our experience. Quantum physics calculates only possibilities. But if we accept this, then the question immediately comes, what chooses among these possibilities to bring the actual event of experience? So we directly, immediately see that consciousness must be involved. The observer cannot be ignored. Observer is part of the description of the world, but the observer is not included in quantum physics. We can only describe the objects, not the subject. So we get the idea that the subject must be more fundamental than the objects. Consciousness is more fundamental.
We don't know in quantum mechanics how to hook ourselves as observers up with the world. We don't know how to treat ourselves as observers as just another part of the physical system that we're describing. The only way we know how to do quantum mechanics as it's traditionally formulated is to keep the observer outside of the system you're describing. The minute you put him in, you get all these paradoxes. And we're forced to say things in quantum mechanics like, look, the book is doing what it's doing because of quantum mechanics, and I see that because I'm there and I see it, and you better not try to analyze that second part of the sentence in terms of applying quantum mechanics to it, because it's going to break down. That's why there are these two separate laws of the evolutions of physical systems. One that applies when you're not looking at them, the other that applies when you are. But that's crazy.
There's no way that we're ever going to mathematize or put into mathematical formula this very act in which a conscious observer comes up with the answer. People say, oh, the measuring instruments, the recorder records it, and there it is, it's on the tape, it's recorded. You forgot one part of the equation. Somebody has to look at the tape. And until somebody looks at the tape, it ain't recorded at all. Until there's an ear, there is no sound in the forest.
The extreme view would be idealism, Bishop Berkeley and the Hindu approach, which says that consciousness is all there is. And that all there is my consciousness. I'm creating you and the camera and the world around me, and all there is me. But that is a view that's impossible to refute, because I can't really prove that you are out there in reality and have your own consciousness, and you can't prove that I'm conscious. So idealism, both from the Western standpoint, from what Bishop Berkeley said in the Hindu tradition, is one possibility. Another possibility, the Copenhagen interpretation says we create reality by an observation collapses the wave function. The problem with that is it doesn't say what observation is. It doesn't say what consciousness is. Why is our brain different from a measuring device or anything else? And it kind of puts consciousness outside science. So my view is somewhere in the middle with the Penrose objective reduction, where you have a superposition which reaches threshold and self-collapses and chooses a reality at that point of a number. It's kind of a multiple choice. It's not like starting from scratch anything you want. It's a multiple choice of multiple possibilities for each specific collapse. But the beauty is, this is one of Roger's great contributions, I think, is that he said the Platonic information embedded in the fundamental level of the universe helps to choose or influences which choice is made. And this only occurs in the objective reduction. So if you make a conscious choice, if you're mindful about it and don't act rashly, or reflexively, maybe think about it and allow yourself to be influenced by what you want to call instinct or intuition or your higher power or the way of the Tao, or may the force be with you, however you want to put it, the quantum information embedded at the Planck scale will influence your decision one way or the other for the good, generally. So it's kind of a way of bringing in some kind of spiritual divine guidance, if you will.
One of the important innovations of quantum mechanics is that a certain fantasy that held in physics up until then about the possibility of observing something entirely passively, observing it without affecting it in the process of observing it. However things turn out, it's fairly clear now that quantum mechanics will have ended that permanently. Looking at things involves interacting with them, and it involves interacting with them in a way whose effect can't be minimized, no matter how delicate your technology is.
Ultimately, science says we have an influence on the observed. Strict separability, strict objectivity, where we can stand back and observe nature without really entering into nature and even modifying nature. That strict separability is no longer possible. We understand that now from quantum mechanics. At the very core of life, the very foundation of experience, it's all created by consciousness. The very earliest experience, the beginning of the universe, you could say, is when pure consciousness, the unified field, seeing itself, creates within its essentially unified nature the threefold structure of observer, observed, and process of observation. From that, at that deepest level of reality, consciousness creates creation.
The observer does have a tremendous impact on what reality is all about. And because of how consciousness works for us as human beings, because of the possible effects that consciousness may have on things that are out there in the world, we can see that there is some relationship between what is observed and what the observer is doing. So if in that regard the observer has the ability to affect what is being observed, then yes, there is some way in which the observer can ultimately impact or affect the thing that you are in fact trying to look at.
The problem with the observer is it the man who makes the breakthrough in quantum uncertainty, for example, Heisenberg's principle. Did a great thing when he did that, because he realized that there was uncertainty that even he couldn't observe, but only as uncertainty. And that only meant that someone else was guiding them to their own chaotic destiny.
When you are not looking, electron can be here, can be there, or can be over there in the corner of this room. But whenever we look, we always find them to be in one Geiger counter.
Quantum mechanics is shot through and through with certain key features. Key meaning that they're critical to what quantum effects are. They undergird the entire structure of matter and the physical universe. They are very well describable in mathematical terms, and they obey certain probabilistic laws that can be written down and seem never to be violated. And yet, they are completely beyond understanding. For instance, what we were just talking about, superposition, and the notion that something can exist in two places at once and yet be in neither of those two places. Okay, well, that's a perfectly good English sentence, I think. But you can't actually make sense out of it. And I can write an equation that basically says in mathematical terms what I just said in English, that gives the probability that if you look, you'll find the object to the left, and a certain other probability that when you look, you'll find it to the right. So that's all neat and clean, and the mathematics of it brooks no contradiction. But to say that before you look, the object is in both places and yet neither. And it isn't that when you look, like lifting a shell up in a shell game, and either the bead is there or it isn't there. It isn't that way. Before you take the shell up, the bead isn't under either shell, and it's also under both. And which one it ends up being, when you pick the shell up, whether the bead is there or isn't there, is not determined by anything, and doesn't actually even come into existence until the moment that you pick the shell up.
It isn't that the particle is in more than one place at once. It's rather that the particle is in a situation in which questions about its position can't even be raised, in which questions about its position don't even make sense, in which asking about the particle's position has the same logical status as asking about the political affiliations of a tuna sandwich, like I said, or the marital status of the number 5.
Particles. Back to particles.
They're not matter, and they're not energy, they're not even in space, they're not even in time. They are patterns which we perceive as a way of understanding what's going on in this realm, this gooey realm that we can't get our hands into. It's our way of understanding. It allows us to make predictions. It gives us a handle on what's going on, but it ain't the whole story by any means.
Answer number 2. Particles aren't really what they seem to be. They're momentary manifestations, momentary poppings of this deeper imaginary realm, this wave-like realm, this implicate order, as David Bohm would say it, this quantum wavy function, as quantum physicists might talk about it, in which there is no particle. There's just this waviness which can spontaneously pop out as particles. So where do they go when they're not in particle? They're in wave world, or in the alternate universe world, where the people in that universe are asking the same question about those particles when they come into our universe. They say, where do they go? The best way I can describe it is, when you ain't looking, it's like a wave. When you are looking, it's like a particle.